Hi, this is Jose Luis, and welcome to another video on this series, Introduction to Parametric Modeling, where I'm going to do a hands-on exercise on taking some random input geometry, like some design geometry, for example, a building or some kind of object, whatever, and perform an operation where we're going to create a serialized way of slicing this object into planar sections. So we're going to cut the object into a collection of sections, more or less sections. These can be for fabrication, this can be for drafting plans of the object, whatever that is. And then once we have those sections, we're going to lay them flat on top of the XY plane so that they have the real dimensions and they could be laser cut, they could be cut into a model, whatever that is. I'm going to do this exercise in two ways. One is going to be like super quick and dirty. It's going to take me 5 minutes. It's going to be super easy to do. But the second version, the improved version, is going to take me a little bit more time because what I would like to do for the second one is make sure that the distancing between these sections fits a bounding box where the distances are not going to be equal, but are going to be correlative to how high each one of these sections is, plus a little bit of a margin that I will be able to control. So that I can lay down those sections without wasting space. Okay, so that part is going to take me a little bit more time of breakdown because it's going to involve some breaking down of the geometrical relationships combined with some data manipulation, etc. So that part is going to be perhaps a little more advanced. So if you don't feel that you're there or you just don't want to sit down through 40 minutes of data matching, then just feel free to skip the second part of this video. Okay, but this is going to be super interesting, and the quick and dirty version is going to be super easy to do. Let's take a look at how to make this happen. Let's get started. So what we're going to do in this exercise is that we want to imagine that we have some kind of like generic shape. So we're going to imagine that this is some kind of building, for example, and that we want to extract the sections of the building, or it can be an object and we want to extract the sections of the object for making it or for fabricating, whatever that is. And this is going to be some general shape. Imagine that this is a blob or whatever that is. The process that we're going to follow to extract a series of sections from this object is going to be actually extremely straightforward. We're actually going to do it in two different stages. The simple, fast, quick and dirty way of doing this is going to be just, for example, creating some kind of axis. So it's actually going to be probably a line, just a simple line. I'm going to take that line and subdivide it into vertical planes. So that's also going to be super easy to do. Then I'm going to use each one of those planes as a section in plane that is going to cut through the object that I have. And once I have all those sections in the 3D environment on top of the actual geometry, then I will do a simple reorientation process like we've done in previous exercises. Well, I will create a sequence of straightforward planes on the XY, and I will reorient each one of the sections back onto the floor on XY. Again, because these will be very useful for drafting plans, for sending this for fabrication, whatever you want to make out of this. It's a very common process to do. I'm saying that this is the quick and dirty version because it involves stuff that is not very parametric, like for example, drawing this line manually and cutting it and then generating planes that are like at regular intervals. But the second part of this video will be, I will try to make this process a little cleaner by making sure that the planes that are generating the cuts for the building are parametrically bound to the object. So they don't have like, you'll see what I mean by that. And then I will also make another optimization, which is the fact that all the planes that the sections are going to reorient to on XY, instead of being at regular intervals, which may leave larger or smaller gaps between the drawings, I'm going to make sure that the distance between them is actually fit to the size of the section so that we have a more homogeneous distribution. I will also show what that means very soon, okay? Now let's go back to Grasshopper and let's get this part done, which is going to take us like a couple of minutes. It's super easy to do. So here we are back. We have some kind of geometry, some kind of complex form that we want to extract the sections for. I created basically this igloo-like kind. It's like a really fancy igloo of sorts, right? And I want to highlight that it's actually hollow. So it has kind of a wall thickness to it, which is going to make the sections a bit more interesting. And I also have this one straight line perfectly parallel to the y-axis that I'm going to be using as the axis for the vertical planes. So I have already dropped here a brep empty parameter box that I'm going to load with this geometry. And remember, just a reminder, this is just one single object. Everything is joined together as part of a Boolean operation. And then here, I'm going to join and I'm going to bring in the curve that I'm using as the axis. Okay? All right, I'm going to stop this and I'm going to hide this. And I have two sliders representing the amount of sections that I want to cut the building on and what is going to be the distance between the drawings as soon as I drop them here on the XY plane. So this is going to be extremely easy. So the first thing that I'm going to do is I'm going to subdivide this curve into vertical planes that are going to be the sectioning planes. So I can go here to division and I'm going to try perpendicular frames, for example, and I'm going to try that. I'm going to say curves and I'm going to say these are the amount of sections. But remember that when I divide a curve into a set of segments, what I get in return is one more plane than the segments. So maybe what I can do is I can do like a quick expression here where I say what I actually want is to be really precise. I want x minus 1. So if I want 20 sections, I need to divide the curve into 19 segments. So that's one thing. Okay? And you can see that I have now 20 vertical planes, and but I do not like the orientation of the planes. You can see that the orientation is like X is pointing up and Y is pointing to the right. I'm not sure that I like that orientation because when drawing it, it's going to be a little messy. So what I'm going to do is I'm just going to remove this and I'm going to create those planes manually myself. So I'm going to subdivide the curve I'm going to subdivide the curve into a family of 19 segments, and then I'm going to place an XC plane on top of each one of these points. So you see that now the plane is oriented with the X to the right and with the Y pointing up, which I think is a nicer orientation. So then I have my planes. I'm going to use these planes as the sectioning planes for this brep. So now I'm going to go to intersections and I'm going to go to mathematical and I'm going to see that I have brep and plane as intersections. So I'm just going to drop this one and I'm going to create the intersections between this brep and all the planes that are contained here in the sectioning planes. And as I do that, you're going to see that I am getting all the sections for each one of these elements here, which is kind of nice. Let me hide this and you can see how if I had the planes as well and if I had all those points, you can see how I have all those sections in 3D, which is kind of nice. I like this. I actually like this a lot. Yeah. So now that I have these sections in 3D, what I want to do is I want to bring them into XY. How can we do that? The way I can do that is by taking, for example, I'm going to create a point. Oh, we have a point here. I'm going to create a point. I'm going to bring it into Grasshopper, and then I'm going to use this point as the center for an XY plane. Okay, and then what I'm going to do is I'm going to create a one-dimensional array of these planes in this direction. So for that, we also already know that one technique that we can use is to move this plane with a collection of vectors that are at increasing intervals. So for example, if I have 20 sections and if I have the distance between the section being 10 units, I can create a numerical series that starts at 0, that has the step size is how far away they are, how many elements is the amount of sections. And then this is going to give me a list of numbers that looks something like this. And if I use those to factor a unit y vector, then what I end up getting in return is a collection of y vectors multiplied by each one of these lengths, and therefore all the vectors for the motion. And now I can just take this and take this, and then I can now move the original plane by this collection of vectors, and then I get all these vectors for the sections. All right? And now I have the original planes, I have the target planes, and I have the sections that I want to move. So I can now reorient all of these elements with a simple orient transformation. So I'm going to go to the transform tab. I'm going to go to the orient category. I'm going to place this here. I want to move all these curves, the sections. I want to move them with this being the reference plane and with this one being the target plane. And ta-da! So what is going on? Oh, something is not right here. All right. What have we said before that we need to take a look at when something is not working exactly the way we want? What is probably the culprit? Who is guilty for this? There's probably some data problems going on. So let's take a look at the data here and how can we fix this. Now, what is the very first thing that we always need to do whenever we have data problems? We need to take a look at the data. So I'm going to place a panel here, and I'm going to take a look first at what's coming in from this plane. So this plane is a data tree structure that has one branch and 20 elements on the list. So that's one thing. The other thing is the other planes that we're working with are following a very, very similar structure. So these two should be good, I think. And what about what's coming out of the component? And also, why is this red? Why is this giving us an error? And why is this saying that the intersection failed? Well, the reason why this is saying that is because, for example, this plane here and these two planes here are not cutting anything, you know? And actually, if I were to plug this in here, you can see that the structure of the data is kind of very interesting. What we have is a data tree where instead of 20 elements, we have 20 branches in this case. And then each branch contains one closed planar curve or two closed. How can we have two closed planar curves? Where, for example, there are situations where here we have two curves, here we have two curves, because the result of the intersection might be more than one curve. And we also have branches that are empty, branches that do not have any data, like the first one, you see the first one, and the two last ones here. That is because the plane did not intersect with the object at all, and therefore no curve was generated. So now that we see that this is a structure, these are the structure of the curves, and this is the structure of the planes, what do you think from those two main data tree operations, which ones do you think we should try to go for? I'm going to give you a few seconds. You can pause this video if you want. I'm going to give you a couple seconds. Think about it. Think about it. Think about it. Tick tock, tick tock, tick tock. Well, we have the two options, okay? So we could flatten everything. So we could flatten this and remove all the complexity of the tree. However, in this case, I don't think that's a good idea because it turns out that we have a different amount of sections than we have of curves. So here we have 21 curves, whereas here we have 20 sections. And that's not going to be a good thing. And also, we also have a situation where some of the cuts don't have a section, so there should be nothing on there. And some of them have two things. So flattening is going to mess things around. So I think in this case, it might actually be better if we take each one of these two data trees, if we graph them so that every plane has its own branch. And then Grasshopper knows that the first branch of planes needs to go with this empty one. The second branch of planes needs to go with this curve here. The third branch of planes needs to go with these two curves here, etc., etc. So that would look something like this. So I'm going to graph this, and then this becomes the new tree. I'm also going to graph this, and this becomes the new tree. And you can see that the structure of the data now looks very, very similar. It looks identical, and that each curve here, or each group of curves, is going to have a matching plane here and a matching plane here. So now I think with those two, now we can now say here and here. And did we get it? Woohoo! Yay! Hooray! It's looking great. And we have the two last planes are empty. They don't have any projection. And this first one here also doesn't have any projection. All right. So that was neat. That was very cool. I think this, and I'm going to clean this up a little bit. Yes. So actually, no, but before we do that, I'm going to keep this tree here because I like, this is a very interesting tree that we're getting here. It's like a very non-standard one. So I'm going to keep it here because I like that we had exposure to that. So you can see that how easy this exercise was. It was basically, what is it, 10 components that we have used? It's like a super, super easy thing. I'm going to group these ones. I'm going to group these ones. And then I'm going to move here, here, and then I'm going to do here. I'm going to group this as well and group here. So the simple version of this exercise was this. But now what I want to do is I want to improve this exercise in a couple different ways. So for example, we did this straight line, but the nice thing about parametric design is that that line, there's no reason why it should be straight. So what if we wanted, for some reason, I don't know why we want to do this, but what if we wanted to find the sections that were kind of like this, you know, the sections of the building that were sort of like this. We can just plug in here the curve. We set this curve, and if we want to make them parallel, then that can work that way. Or if instead we want to make sections that are perpendicular to the actual curve, we can go back to the method that we were using before. So I'm going to plug in here the curve. I'm going to plug in here the amount of cuts, and then I'm going to use these frames here to fit this. And you can see how the cuts are now kind of all wacky and are following the perpendicularity of the curve, which is kind of cool. I'm not sure how useful this is, but it's kind of cool. And what's nice is that the orientation of the planes ended up being really nice as well. So we have here now these planes all the way here. So that is working well. However, I'm going to go back to the straight line just because, that's probably a more realistic scenario at this point. And this one and this one. So that's something that we could try. But most importantly, what I would like to try is to improve this exercise for the following reason. As you can see, the way we have done the line here, there's like a few gaps here. So there are planes that don't have sections. And I would like to make a definition that guarantees that we always have cuts. We always have sections because the sections are fitting perfectly the boundary of the object. So that's one thing that I'm going to do. The other thing that I'm going to do is the fact that if I look from the top view, you can see that this section is kind of small. This one is also small, so there's a lot of gap here. These ones are bigger, so the gap is not so much. So if I could maybe shrink this, but now I'm shrinking all the way to the maximum and I still have a big gap here. So maybe what I want to do is I want to distribute these planes so that their distance is not always the same, it's different, but that distance adapts to how tall that section is. And maybe even add a little bit of a margin. That could be interesting, so that we get like a more fitted, like a more, like a distribution of these sections that is according to how big those sections are, not to just some arbitrary number that we set. So follow me up because I'm going to extend this exercise and I'm going to improve those two aspects to make everything a little more parametrically tight, which, as you know me already, I like those things. Let's take a look at the whiteboard and how we could make that happen. So, piece of cake, super easy. Remember how we said that we just took this arbitrary line that we drew and then we used that to generate vertical planes and cut the sections of the surface? Well, we're going to forget about that. Oops, sorry, I don't know what I turned on. We're going to forget about that and we're going to follow a more parametric way, which relates to generating those planes in a way that has a better logic depending on the shape of the object. And the way that we're going to do that is that we're going to find this thing that is called the bounding box. The bounding box is basically a box that is fitted to exactly the shape, exactly to contain absolutely, but in the most minimal way, a particular geometry. What that would mean is that the sides of the box are going to be touching the edges of the geometry on the X and Y and Z directions, and therefore it's going to be fitting it perfectly inside. And then once we have that box, then it's just going to be as easy as choosing one of the edges and then subdividing that edge into planes so that the first and the last plane are going to be perfectly tangent to one of the ends of the drawing, but all the rest of them inside are going to be cutting the geometry. And then once we have those planes, we feed those planes into the rest of the definition, and then we're good to go. So we're going to start with that, and then we will talk about how to move the planes to XY. So back here in Grasshopper, I have turned off all the other geometry, etc. And I'm going to focus here only on this one, on the geometry. I'm going to show the B-rep here so that we can all see it clearly. And actually, now let me hide it from here and let me turn it on here so that we can see it a bit more clearly. Correct. And then what I'm going to do now is, remember, I'm going to create a bounding box that is going to contain perfectly this object. The way I'm going to do that is that I'm going to go to primitives. And in primitives, we actually have boxes that are oriented in a way that it contains a particular geometrical object. So I'm going to click on bounding box, and you can see that the input is a geometry that I want to contain, and whether if we want to orient that box in a particular angle. So I'm going to stick with the global XY, which is going to be enough. And then you can see that as I plug that in here, you can see that this box is containing perfectly my object in, it's like touching in just with the one point at each one of the four of the six sides of the geometry. I want to highlight how this component, the input, is of the type geometry, so this swirly kind of hexagon here, and that is because we can create bounding boxes for B-rep, for surfaces, for curves, for a collection of objects, etc., etc. And here the output is a box. So now we have the box, and what we need to do is we need to figure out how to take, for example, this line here. If we go to analysis, there's actually a bunch of components that could help us here. We could, for example, use the B-rep wireframe, which if we plug a box, you can see that it gives us a list of the 12 edges, and then we would just simply have to use list item to cherry pick from this list the one that we want. So for example, let's try that out. So I'm going to say list item, I'm going to plug this in here, and I'm going to plug here I'm going to plug here, so you see how 0 is this one here, then 1, 2, and 3, so it would be number 3, the one that we want. So I would substitute this with a hard-coded 3 so that we know that it's always going to be that one. And then we could plug this in here, and then we already have all those planes and then all the sections for my building. So that could be one way to go. Another way to go about this could be, for example, could be taking box corners. So as I do that, and as I deconstruct the bounding box, I can get the 8 corners, and it turns out the corner, I believe which one it is. So point, let me see, I'm going to plug this in here so we can see that I'm going to, where are the planes? I want to turn everything off. So we can see that point A is one of them, then point B is not, point C is not, point D is the other one. So I could create a simple line between A and D, and then I have the line that I wanted, and then I can plug that in here, and then everything is going to work. I have the planes, and I have the sections, and everything works exactly the same. There's no real advantage between one method or the other. Perhaps this one is like slightly more optimal because I don't have to generate 12 lines and then only take one. Any process that means generating a lot of stuff and then discarding a lot of stuff, in general, it's a little less efficient than generating, I mean, I'm generating 8 points here, arguably. So, but points are more lightweight than lines. It doesn't really make a difference. And you can see that performance-wise, I am not getting any one of these like, I'm not getting any one of these profiler pop-ups telling me that this is taking like however many milliseconds. So we're good. So both are pretty much the same. So I'm going to go for this one just because I like it a little more. It's a bit more elegant. It's cleaner maybe. So I'm going to just keep this one here. All right. And then I'm going to plug that in here. And then I get my sections. I'm going to turn off this and my sections are there. And I'm going to turn off the planes and everything looks good to me. So now it's going to be a matter of figuring out how can I take these sections and lay them flat here in a way that they are respecting their relative heights. Let's go back to the whiteboard and figure out how to do that. Okay, let me try to explain this with a couple diagrams and buckle yourselves up, hold yourself up to the chair because I need your 200% attention because this might be a little confusing, okay? So bear with me. What we want to do is the problem that we have here is basically that we have a few sections in 3D space named from 0 to 2, for example. Let's say we have 3. And then what we want to do is, and each one of those sections may have a particular height. So it might be however tall in the C direction, that doesn't matter. So what we want to do is we need to figure out a way of arranging a collection of planes in XY so that the distances between them are so that these sections, when placed on top of them, they have the exact dimension, the exact C dimension between them here. So this dimension and this dimension are the exact dimensions for the height of this section and the height of this section, correct? So the challenge here is basically figuring out what are the distances between these planes and how do I create them. So that's what we need to find, okay? Now it's going to be a little confusing because we need to do a little bit of like changing this around for the following reason. Think about this, think about how we have the problem set up. We do have, we know that the planes are arranged between them. We know that if we have 3 sections, we need to create 3 planes. And we know that the distance between the first plane and the second plane equals the height of the first section. And we know that the distance between the second and the third plane equals the height of the second section. And for the last section, we don't really need another plane on top of it, so we don't need to care about that. Now, the question is, because I need to place these planes in XYZ space, what is the y coordinate? What is the y coordinate of each one of these planes so that I can generate a numerical sequence and then place this in space? So let's imagine that this plane had an I coordinate of 0. So we start from 0 and then we just need to figure out the y coordinates of each one of them, of the rest of the planes. The way we can go about this is by thinking that if we have 3 planes, each one of them having an index number, and that we know the height of each one of them, the challenge is creating a new set of numbers that is going to define cumulatively what is going to be the y coordinate of each one of the planes. So I can say here, I can go here and say, well, the y of the plane, how do I calculate that? Well, it turns out that for the first plane, I know that it's going to be 0, or whatever the original plane is going to be. For the second one, for the second plane, it's going to be the height of the previous one. So you can see here that for the second plane is going to be the height of the opposite section. So you can already see how we have to here add an artificial 0, which doesn't come from anywhere, and that the y-plane on the second position equals the value of the height of the first position. So you can already see how we're going to have to do some kind of shifting of lists, something like that. We'll see. But then, so the coordinate of this one is going to be 3. But then what is the coordinate of this one? The coordinate of that one here is going to be the addition of the heights of all the previous numbers. So 3 plus 7 is going to be 10. And therefore, the y-coordinate of this one is going to be 10. And if we had to place here another section, because this distance would be 4, the coordinate of this one would be the addition of all of this, if we had them, which we don't have it here, which would be 14. But you can see how basically each one of these numbers is the cumulative height of all the previous ones except for this one. You see? You see where I'm going with this? So, long story short, what are we going to have to do? First of all, we're going to have to create a list. Our target is to create a list of all the y locations of each one of those planes. And then we're going to first start with an artificial 0. And then we're going to have to do cumulative additions of all the heights of all the sections that we have on our sketch. So, I hope this was clear. I'm not sure how to explain it in a different way, but then maybe by watching how I do it in Grasshopper now, maybe we can get some clarity about that. Let's go to Grasshopper and let's figure out how to implement this that I just described here. Okay, I'm going to do this very slowly, one step at a time. We're going to go back to the whiteboard, and this is the first thing that we need to figure out. We need to figure out first the height of each one of the blocks of the sections. So I'm going to go back to here. I'm going to hide this so that I can see the geometry a bit more clearly. And if I will, maybe I want to turn that on, or maybe I don't. Maybe I just want to keep the sections here. So the first thing that I need to do is I need to figure out the height of each one of the sections. So for that, I'm also going to use the boundary box. So I'm going to the bounding box. So I'm going to go to surface, primitive, bounding box. And then for each one of these, I'm going to calculate the bounding box. But this is not going to work because you can see that what I'm getting is like several bounding boxes per collection of sections. So for example, you see how for these two sections I get two different bounding boxes, and I actually don't want that. I want one bounding box taking everything inside. So if I zoom into this component, you can see that it has this thing here called per object. So I can right click on the component and then click on this option, which says that when it's checked, instead of doing bounding boxes for every single object, it does one bounding box for all the elements that are inside of the list. Okay? So that is going to be, it's going to give me a data tree that has all the boxes, and each box contains all of the sections. All right. So that's great. And then I need to figure out the height. How do I do the height? Well, it's going to be not very complicated. There is in analysis, there is a component that is called deconstruct box. If I do that and I place this component here, you can see that it gives me the It gives me like the plane for the box, but it also gives me the X, Y, and Z domains of the box. What does that mean? The domain means that the box is somewhere placed in XYZ, and therefore it doesn't just give me the length, it gives me where the box starts and where the box ends. And if I actually were to show this, and if I were to move the surface like farther up, you could see that it doesn't really give me the length, it gives me the Z coordinate of where the box starts and the Z coordinate of where the box ends. Because this is a domain, remember, that has a start and an end, what I can do to actually calculate the length is I can go to domains, I can deconstruct the domain, getting both the starting values, getting both the starting values, which are the same for all of them, and then the end values, which are different, and then just subtracting from the last element, subtracting from the last, the beginning, and then that way I'm going to get a list with all the lengths of each one of these elements here. Can you see that? One problem that I'm carrying, though, from the fact that the first and the last planes were perpendicular, were absolutely tangent to the geometry. I'm going to move this back down. From the fact that the first and the last planes were tangent to the geometry and therefore did not generate any kind of intersection, so the first one and the last one are empty branches. One problem that I'm still carrying from there is the fact that for calculations, the first branch and the last branch are always empty. Because if you look here, you can see how this box, for example, the bounding boxes for the first collection and for the last collection had null items here. This is going to carry me problems. I'm going to accumulate problems by the end. So what I would like to do right now is I would like to take this data tree that has some boxes and some null boxes, and I would like to replace those null boxes with some value that I can use later for calculation. So because what I'm trying to do is calculating the heights of each one of the section groups, what I'm going to do is here, what I'm going to do is I'm going to try to replace from these nulls, I'm going to try to replace them with the value of 0. So for example, I'm going to go here to lists, and you can see that there's a component that says replace nulls with other data. So I'm going to place that here in the middle. I'm going to take this as the input. R is going to be the item that I want to replace. So I'm going to do a hard-coded 0 here. And then you can see that the output is now a 0 here and another 0 on the last branch. I'm going to feed this now back to my calculations. And you can see that now my calculations have a 0 here and they also have a 0 here, which is very nice because it is true that for those sections, I do not have any height there. Okay? Wonderful. So I'm going to just to make sure that I'm going to make sure that these are clearly the section heights. All right, so this is what I got here, and this is how I'm calculating those sections heights, and this is correct. Okay, beautiful. Then what is the next thing that we need to do? The next thing that I need to do, according to the diagram, is going to be figuring out what are the y coordinates of each one of the planes. Okay? And this is because if you remember, when we generate the planes here in order to drop this, what we typically do is we take one plane, one original plane, and then we create a numerical series, and then we copy that plane by a sequence of numbers. All right? So that sequence of numbers now is whatever, but this one is going to be now the one that we are going to generate as the y coordinates, so the green list that I have in there. So how are we going to do that? I am going to copy this here. I'm going to create the xy plane here. Okay. And what I'm going to do is going to be the following. Remember that the list of y coordinates for the planes was, first, it was the cumulative heights of adding, for each one of them, adding, this is all the heights added, this is all the heights added, this is all the heights added. So it is a list of incremental additions of all those numbers. How can I do that with the section heights? Well, I could do that with for loops and other techniques that involve some coding, but it actually, here in Grasshopper, in operators, I have this really handy component that is called mass addition. What mass addition does is that it takes a list of items and it adds them all together. So what does that mean? Let me plug this in here and let me compare the inputs and the output. The result is actually nothing, because remember that components work at the list level. So this component is trying to add all the elements on this list, which is just 0, all the elements on this list, which is only 3, so the result is the same. So what I need to do is I need to flatten all these numbers into a one continuous list, so that when I add them together, the result is 77 point something something. But this result is very useless. What is super useful with mass addition is that the output also gives me the partial results of these additions, which means that for every calculation, it gives me the addition of this element and all the previous ones. So you can see how for 4, I get 7, which is 4 plus 3. 4 and 3 is roughly 12. 5, 4, 4, 3 is roughly 17. 4, blah, 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 is roughly 22. So here I get that list of all the elements added one after the other. So that would be, on our sketches, it would be this list of elements here. Don't get confused by the fact that we have a 0 here. This is an unfortunate consequence that is going to make things very confusing, but this is just because the first section happens to not exist. So we have an additional 0 to deal with, but we still need to take our list of all the massively added numbers, and then we still need to add a 0 at the beginning. So how does that, okay, so let me actually not do that so that we can see how this would work. So let's say that I use these numbers to create all the vectors to move the planes. So I'm going to now use these numbers to generate the y vectors, and then I'm going to move this plane, the original one. I'm going to turn this off, sorry. I'm going to move this plane, the one that I use for reference, and I'm going to move this plane by all these vertical planes. And you can see how very nicely I have shorter, larger differences, and then shorter again, which kind of matches the fact that these sections are shorter, these ones are bigger, and these ones are shorter. So I think we are getting closer. Now, what I need to do is I need to now use those planes that I created here to do the orientation. So I'm going to orient all these planes, so all these sections, I'm going to orient them from their original planes to the new target planes that I have defined here, which are going to be these ones here. And you can see that I have something weird, a lot of problems here, and that is because if we look at the structure, remember these are all grafted, but the data that I have here is flattened. So I need to graft that data and I need to feed it in here, grafted. Okay? And you can see that it's already working, except for the fact that you can see how this is not really working because there are some overlaps here. You can see that there is an overlap here. There are clearly some overlaps here, and there is a missing plane here. So that is, again, and if I do a parallel process, let me also flip not just the sections, but let me flip also the bounding boxes for the heights. So let me flip here all these bounding boxes for the height so that we can clearly see them. You see, you see, they have like these like serious overlaps on top of each other. So that is because I have not added this trailing zero that I was discussing before here. So how am I going to do that? Well, here under mass addition, after I flatten the tree and I have all my numbers one after the other, I just need to add another zero to the beginning. So what I'm going to do is I'm going to take this component that is going to merge two data streams together. And the first data stream that I'm going to merge is a single list with the value of 0. So that's going to be 1. And the other one is going to be this flattened tree. You can see that the result now is going to be the same list, but with a 0 on the beginning. And then, are you ready for this? Are you ready for this? And then as soon as I plug this in here, now all the sections are like perfectly set one after the other, with the exact heights and super snug, like really perfect, like a really nice perfect fitting. Wait, but maybe it's too much. Maybe they're fitting too well. What if we added like a tiny bit of a margin inside of here? Well, that's just going to be as simple as taking all these numbers and adding like a small value to each one of them before they get added together. So here, before we flatten the tree, I'm going to add, for example, 0, boom, I'm going to add these values, I'm going to add this, and then I'm going to plug this in here. And now we have this tiny margin that we can use to put them all together, or just to give them like a tiny bit of spacing between them, like 0.1, for example. And with that, I'm going to turn off this. I'm going to turn off the planes. I'm going to turn off like all this stuff. And I'm actually not going to turn off the plane. I like to see this. And I'm going to turn, what am I going to turn off? I'm going to turn this off. And I think with this, ta-da! This is what I wanted to get to. Okay, I think this is where I wanted to finish this exercise. I honestly did not think that this part was going to be so convoluted, maybe, if you will. I don't know. But I think it was actually a really interesting exercise and a fairly advanced one on data manipulation and geometry conceptualization. Anyway, I hope this was useful. This idea of sectioning an element and laying it out in a way that it fits really well so that we don't waste material when laser cutting it or 3D printing it or whatever. It's actually a very common one. So I hope that was useful. Thank you very much. I will see you on the next videos on this series. More learning, more hands-on exercises. And in the meantime, maybe you want to like this video. Maybe you want to leave a comment. Maybe you want to subscribe to the channel. All those YouTube things that we do in modern world life, whatever. See you on the next video. Bye bye. Thank you.